Come back. In my previous video, I had seen Liouville's theorem, extension of Liouville's theorem, some application based on Liouville's theorem and extension of Liouville's theorem. Today, we all of us know what is the statement of maximum modulus theorem. If fz is analytic function inside and on a simple closed curve C, then the maximum value of modulus of fz occurs on the boundary of this curve unless fz is constant. That means if maximum value exists in the interior point of this curve, then the function always would be constant. This is the maximum modulus theorem. In my previous video, I had seen this theorem elaborately. Today's goal, today I will see at first two results based on maximum modulus theorem. Then I will see actual goal of this lecture. Today's actual goal of this lecture, today I will see zeros of an analytic function. I will see what is the zeros of an analytic function. Briefly, this is actually goal of today's lecture. Okay. Now first see what is the result based on this theorem, maximum modulus theorem. First application, let G be bounded region and function f is continuous on this region. If we consider this is Z, it is continuous on this Z closure, means whole Z, also included boundary. If fz not equal to 0 anywhere in this Z closure, then modulus of f has minimum value in this Z closure, which occurs on the boundary of G and never in this interior. At first, I will tell you try oneself, then see my solution. This is actually statement of maximum modulus theorem. Just think. Okay? Let's see the solution. Here I will apply, since given fz not equal to 0, since the image is non-zero, so here I will apply for 1 over f. Since given f is continuous on z bar, that means obviously 1 over f is also continuous on z bar. Also given f is analytic, so 1 over f is analytic and non-constant on G. That means 1 over f is also continuous and 1 over f is analytic in G. And since f is non-constant, then 1 over f also non-constant. Therefore, by maximum modulus theorem, we can tell 1 over f has maximum value on the boundary of G only by maximum modulus theorem. Since 1 over f has maximum value on the boundary of G, that implies modulus of f has minimum value on the boundary. I hope my all viewers have understood this is clearly. Here minimum value exists on the boundary since given the image is not equal to 0. Actually, this is the statement of maximum modulus theorem. Okay? Next, question which is also depends on maximum modulus theorem. Here Pz consider be a polynomial z to the power n plus a n minus 1 z to the power n minus 1 plus up to a naught, where a naught a1 up to a n minus 1 are complex number, and let qz equal to 1 plus a n minus 1 z up to a naught z to the power n. And if modulus of pz less than equal to 1 for all z belongs to C, with the condition modulus of z less than equal to 1, then which of the following statement is and are true? Option 1, here given modulus of pz less than equal to 1, that imply modulus of qz less than equal to 1, and this is true for all z belongs to complex number with modulus of z less than equal to 1. Option 2, q is a constant number. Option 3, pz equal to z to the power n, where z belongs to complex number. And option 4, p is a constant polynomial. Which of the following is a true option? And at first try to ownself. This is very basic question. Just depends on maximum modulus principle. Then see my solution. Let's see the solution. The question notice about qz. Since p and q both are polynomial, so obviously there are entire. And norm f infinity means, we all of us know this is actually the supremum of fz, where modulus of z less than equal to 1. Then norm q infinity, since the question about the q means supremum of qz such that modulus of z less than equal to 1. This is the entire function and polynomial, non-constant polynomial. So obviously by maximum modulus principle, we can tell this supremum value exists always on the boundary. That means here would be modulus, actually this would be modulus of z equal to 1, because the maximum exists only the boundary. Now put the value of qz. Qz means 1 plus a n minus 1 up to a naught zn, such that modulus of z equal to 1. Then if we divide it by 1 over z to the power n, supremum of 1 over z to the power n, then this value would be z to the power n plus a n minus 1 z to the power n minus 1 up to a naught, such that modulus of z equal to 1. Here I have divided by 1 over z to the power n, because this is varies on the modulus of z equal to 1. And in this boundary, modulus of z and modulus of 1 over z, always this value is same. So we can always divide by 1 over z to the power n this equation. And this is actually nothing but, notice, this is actually the pz polynomial if we divide 1 over z to the power n. And since here this is value for modulus of z equal to 1, so this is actually, this value would be 1. So this is actually supremum of z to the power n plus n minus 1 z to the power n minus 1 up to a naught, such that modulus of z equal to 1. And this is actually the polynomial phi infinity polynomial. And since these two polynomial are same, actually I have got, and since given if pz less than equal to 1 for z belongs to complex number with modulus of z less than equal to 1, that means as norm p, since here I have used supremum norm, this would be less than equal to 1. Since this is less than equal to 1, and I have got Q infinity norm and P infinity norm are same. So that imply Q infinity also less than equal to 1. Q infinity less than equal to 1, that means Qz is modulus of Qz less than equal to 1, and this is true for all z belongs to complex number with the condition modulus of z less than equal to 1. So Qz less than equal to 1 for all z belongs to C with the condition modulus of z less than equal to 1. This is right option. Option 2, Q is a polynomial, constant polynomial. Is it true? The polynomial Qz is this, and Q0 equal to, notice the polynomial, Q0 equal to 1. Notice, since Q0 equal to 1, and here I have got norm Q infinity means supremum of Qz, this value is, since I have got norm Q infinity less than or equal to 1, and also I have got Q0 equal to 1, that means by maximum modulus principle. That means by maximum modulus principle it is implied Q is a constant polynomial. This is constant because its maximum value exists at the point 0, which is the interior point. I hope my all viewers have understood why I have told you the maximum modulus theorem is very important. By the statement of maximum modulus theorem, we can tell the Q is a constant polynomial because its maximum value exists on the interior point of the curve. Because by statement of maximum modulus theorem, when a function be non-constant and an analytic function, then its maximum value always exists on the boundary. Okay? So, therefore, since only value of Qz is 1, therefore, all coefficient a0, an minus 1 all will be 0. An minus 1 up to a0, this value would be 0. So, notice the option Qz is a constant polynomial. This is right option. Next option, all coefficient an minus 1 up to a0 equal to 0, and I have got norm Q infinity is equal to norm P infinity, and in Pz if all coefficients equal to 0, that means that implies Pz equal to z to the power n. So, option 3 is also right option. Pz equal to z to the power n, this is true for all z belongs to complex number. And option 4 is a wrong option. P is a constant polynomial. This is wrong option. I hope my all viewers have understood. Okay, see our actual goal of this lecture. Zeros of an analytic function. Zeros of an analytic function. Actually, this is a point such that f of a equal to 0 and z of a, which is actually the collection of zeros of an analytic function. This is the set z in G such that f of a equal to 0, where a is the 0 of the analytic function. And the idea is, suppose f is analytic on the neighborhood BAR, this is A and this is R, and suppose fa equal to 0, then by Taylor's theorem we can tell fz equal to cn z minus a to the power n, where cn equal to 1 by n factorial f to the power na. Since given f of a equal to 0, that imply, since f of a equal to 0, that imply c0 equal to 0. That means at the point A is the zeros of analytic function, and this is called simple 0. And there exist two cases arise. Case 1, if all derivatives of f at the point A are 0, then f is called identically 0 function on the set BAR. That means if on the set BAR all derivative of f, that means f dash a, f double dash a, f triple dash a, so on, all derivative are zeros, then f is called identically 0 on the set B of BAR. So if not, if f dash a, f double dash a, all derivative not be identically 0, if m be the smallest positive integer such that f to the power m at the point A not equal to 0, then fz equal to z minus a to the power m summation n equal to m to infinity cn z minus a to the power n minus m for z belongs to BAR with first term Cm not equal to 0. Then we can tell in this case that means f of a, f dash a, f double dash a up to f to the power m minus a equal to 0. But f to the power m at the point A not equal to 0. In this case, f is called 0 of order m at the point A. Otherwise, if m equal to 1, then this is called simple 0. I hope my all viewers have understood what is the simple 0, what is the higher order 0. Okay. Now let's see some example. First example, fz equal to sin z. In sin z, at the point n pi, the function is fz has simple 0 because why simple 0? Because sin z equal to 0, we all of us know this is 0 only the point z equal to n pi, but ddz of sin z equal to, we all of us know, cos z, but cos n pi, this is not equal to 0. So obviously that implies f has 0 of order 1. But next, fz equal to sin squared z. For this, if we consider fz equal to 0, then that implies sin squared z equal to 0, and sin squared z equal to 0 at the point z equal to n pi, the value of sin squared z is 0, we all of us know. Now I will see what is the order of this 0. If we consider f dash z, then this value would be 2 sin z cos z, and 2 sin z cos z means sin 2z, and we all of us know f dash n pi means sin 2n pi, which is equal to 0. But if we consider f double dash z, then this value would be 2 cos 2z, and f double dash n pi, this value would be 2 cos 2n pi. That means this value is 2, which is not equal to 0. That means fz equal to sine square z has a 0 of order 2. I hope my all viewers have understood. Okay. Next example, that means similarly if we consider z to the power 100 sin z, then z equal to 0. Obviously z equal to 0 is a 0 of order 101. Similar to z sin z, if we consider z to the power 100 sin z, then z equal to 0 is a 0 of order 101.